Virtue number 2, and we're going to be talking about graph coloring problems. What is graph coloring? Graph coloring refers to the problem of coloring vertices of a graph in such a way that no two adjacent vertices have the same color. This is also called the vertex coloring problem. If coloring is done using at most m colors, it is called m coloring. The minimum number for colors needed to color a graph is called the chromatic number. Normally, we need a minimum of 2 colors to make a graph coloring problem. Now, for example, the problem of finding a chromatic number of a given graph is NP complete. This says that graph coloring is born of both a decision problem as well as an optimization problem. A decision problem is stated as with given m colors and graph G, whether a such color scheme is possible or not. The optimization problem is stated as given m colors and graph G, find the minimum number of colors required for graph coloring. Graph theory is one of the most important topics of computer science. It carries a great significance in algorithms and data structures, and it is an indispensable part of many problem solvers in programming. Among so many parts of graph theory, one interesting and easy to understand subtopic that could be solve a lot of problems in the real world is a graph coloring that we are going to discuss. Now, what can be some normal applications for the graph coloring problem? Well, there's a lot, but we're going to have 4 more general ones. One can be a design of timetable, another can be a Sudoku. We can register a location in a compiler, a SAM scaling tool, a math coloring, that is the most common one, a mobile radio frequency assignment, maybe a frequency assignment in different radio stations, or finding out no-index registers to store variables temporarily during execution of loop. This is just one of the many, but in this time, we are going to register in algorithm of 3 different implementations.
I want to talk about brute force algorithm. Here we have the brute force method for the same problem, that is graph coloring. This approach evaluates all possible combinations to find the best solution, guaranteeing optimal results but at a very high cost. On the left, example with a small graph illustrates how this strategy assigns colors. However, the execution time to results on the right clearly shows that as the number of nodes increases, the time skyrockets exponentially. Although this method guarantees the optimal solution, it becomes impractical for large problems due to its high computational cost. This is why in practice heuristic algorithms are preferred for large-scale applications. Now, let's talk about heuristic algorithms for graph coloring. Unlike exact methods, heuristics aim for fast and reasonably good solutions, so not necessarily optimal. In the image, we see an example of graph coloring using a greedy algorithm. On the left, the execution times indicate that this method scales well as the graph size increases. Additionally, the bottom chart reinforces this idea, showing significantly lower execution times compared to more expensive methods. This approach is useful when working with exact solutions is too costly in terms of time and computational resources.
What is a genetic algorithm? A genetic algorithm is an optimization method inspired by biological evolution. It works through selection, crossover, and mutation to iteratively improve solutions. The goal is to assign colors to graph nodes so that no two adjacent nodes share the same color. The algorithm follows these steps. A population of random solutions is created. Each solution is assigned based on how well it minimizes conflicts between adjacent nodes. The best solutions are chosen, and 2 solutions are combined to create new ones. Small changes are made to explore more possibilities, and the process is repeated until the good solution is found or maximum number of iterations is reached. The graph shows that execution time increases with graph size. For 10 nodes, the time is low. The, for 15 nodes, the time is moderate. The 100 nodes execution time is significantly higher. How we can effectively solve a graph coloring problem? There are three main approaches: brute, brute force, heuristic algorithms, and genetic algorithms. Each has advantage and disadvantage. Let's see how they work and which is the best for different cases. The brute force approach tests and possible combinations until it finds the best solution. It guarantees optimal resolutions, but execution time grows exponentially, making it impractical for large graphs. The heuristic algorithm uses intelligent strategies to find approximate solutions, and genetic algorithms mimic natural evolution, and they create initial population on solution and apply selection. Crossover or mutation improve over the time.
So now let's proceed with the practical case. We use the graph coloring problem to color a map, in this case the map of Baja California, which has 7 municipalities. And the goal is that each municipality has a different color and that no adjacent municipalities share the same color. So in our graphs, the nodes represent the municipalities and the edges represent the border that the municipalities share with each other. So now if we look at the graphs, we see that the brute force algorithm first. We know that this algorithm has to explore all possible color combinations and then take the optimal solution. It will guarantee that we have the correct solution, but unfortunately it takes a lot of time for large graphs. In fact, we did try to apply this algorithm with the 32 states of Mexico, but the time was really long that we couldn't finish the experiment, and we had to move on to a smaller sample size. And if we compare it to the heuristic algorithm, we know that the heuristic algorithm will give us a fast execution, will be faster, but might not give us the best solution. But if we compare it to the genetic algorithm that is in below, we see that they have almost the same result, but the only difference will be the time. Genetic might be slower than heuristic. And overall, the genetic approach will give us better solutions with time than compared to heuristic that will give us good solutions, but not always the best. So genetic algorithm is better for large and complex problems, and the heuristic, in this case, like ours, it is better for practical uses.
In this moment, teacher, you see the final conclusion in general, but I think this analysis confirms that the heuristic algorithm, especially gradient coloring, is a strong and practical choice for handling large graphs, even as the number of nodes keep increasing. While it doesn't always guarantee the most optional solution, it offers a good balance between speed and efficiency, making it ideal for real-world applications, where finding a fast and acceptable solution is more important than waiting for the best one. I think one of the biggest advantages is the that it works in polynomial time, meaning it remains efficiency and even for complex graphs. And plus, its performance can be improved by using smart ordering techniques such as largest first or smallest last, which help reduce the total number of colors used. While it may not compete with more advanced algorithms in terms of optimality, I think it simply and scalability make it a gold method for many practical scenarios, from scheduling problems to network optimization. I think in the end, query coloring proves to be reliable, adaptable, efficiency solution when dealing with large scale graph, striking the right balance between computational costs and usability. Thank you.